Hey everyone, welcome to a new video. It's Federico here, and today we are going to see how to do this. So basically how to create a bunch of shapes and create with jit.gen an algorithm that will orient them always toward a certain point in space, a target we will call it. So if you find this interesting, stick with me and let's go into it. So let's start. So first thing, I will take my JIT world snippet, which contains the JIT world and the camera. A snippet is just a bunch of max objects that you save together through this icon here, save snippet, and it's super convenient because you can then recall them by this literal icon here. So you go into snippets and you search for your snippets that you want to use, and then you just drop it inside the patch and will recreate the objects that you saved when you created a snippet. So super useful. So what I got here is just a JIT world with the full scale anti-aliasing, size, floating, raise color, sync 0, FPS 60, enable 1, and a camera, blah blah blah, that just looks at the center with tripod, and a titanium drive to move around the camera using my keyboard. And then I also got a snippet to recall the Photo Studio environment skybox. So it's just a GGL environment with the file that is built in Max called the Photo Studio Loft All 2K AXR. If you don't want to copy that file path, you just go into the file browser, you look for EXR, and you will see that there is one that is built in Photo Studio Loft All. You just right click, copy file name, and then you just paste it inside the GGL environment object. And the skybox, we use this file to make a skybox for the scene. Super cool. And then we can move around using the keyboard because our camera has titanium drive attached. Very nice. So now what we need is legit noise to put our particles in the space randomly. So JIT noise 3, float 22, let's say that we want 100. It's not really particles, we're going to use actually cubes. So this is the amount of cubes we will have. And then we need a jit.gen for the actual algorithm. So let's give it a title and call it face toward target. All right. And then we need a GGL multiple because we're going to render those cubes using GGL multiples. So it will going to draw to main. It has 3 parameters. So GL params. First is going to be the position. The second is going to be rotate. And pay attention, this is not rotate x, y, z. It's not this attribute. It's the rotate attribute, which is different. And then we need the scale. So how is the rotate attribute different? Well, the rotate attribute takes as arguments the angle and then an axis of rotation. So we'll get the axis x, the axis y, and the axis zeta. And that's exactly what we need for this algorithm because we will provide the axis around which the objects have to rotate to face these the target. It could be done in 1,000 different ways, I guess, but this is just kind of the easiest way I found to do that. So that's the attribute we're going to use. And just for completeness, just remember that rotate x, y instead just as 3 angles as arguments. Okay, so pretty much different. Okay, cool. Now we need a GGL grid shape to render as our cubes. Target for the GGL multiple. So GGL grid shape main, let's set it to automatic 0. Let's set the color to white or something, and that should be it. Connect it here. Cool. Then we connect the first output of jit.gen to GGL multiple. Let's connect the JIT noise. Before we connect the JIT noise to jit.gen, I want to do something, which is I want to create another jit.gen, and this is only used to initialize the position, so we can call it like Init Position or something. And then I want to send this new position inside a JIT matrix that we will continuously bang from our JIT world middle output in order to provide the animation for our cubes objects. So let's create a bang here, which is actually going to be a load bang. So let's create actually a load bang. So the initialization will happen when the patch is first loaded. And inside the init position jit.gen, I want to just rescale. So scale minus 0 to 1 between minus 1 and 1. Or, as I learned from Matteo Marson, we can do it in a much cooler way, which is to just mix minus 1 and 1 using the input as the mixing factor. So now the cubes will be all around in a minus 1 to 1 range. So let's give it a go. It will not work at the moment because we're using scale as a parameter, so the cubes will not be rendered because the scale is 0. But if we take away the scale attribute, you can see that we have a bunch of sphere. It's not really cubes at the moment. So let's give it the shape argument here and call it cube. All right. Let's maybe make this range a bit bigger. So instead of mixing between minus 1 and 1, let's mix between minus 4 and 4. And then we have a bunch of cubes. Cool. I would like to apply a material to those cubes. So I will go with the GGL PBR physical base rendering and we'll draw to main. And as a matte diffuse, let's use white, which is the same color I wanted the grid shape to have, but we now need to attach it to the PBR in order for it to work. And I will connect it both to the, whoops, wrong inlet, both to the GGL multiple and to the GGL grid shape for it to work. Okay, cool. So now the cubes are using the environment, the skybox, as a kind of factor that influences their color. So that's pretty cool. It's like they're reflecting the light from the scene. And cool, let's get back with the scale attribute here. Let's go inside our jit.gen with the actual algorithm, so face toward the target. Let's create another output, and this is going to be our scale. So I'm going to attach a comment to it and call it scale. Let's check the Max console once in a while to see if I get any errors. Since I'm too lazy to double click on jit.gen, I will just use the open message to open it. Cool. So we wanted to have a scale, and what I will do with the scale is to set like 0.25 for the x, 0.35 for the y, and I guess 0.1 for the zeta. So they will look more like parallelepipedy. This is the word. So basically like rectangles, but in 3D. And I'm going to attach this to the scale. So if I load bang here, now you can see that they all have the same scale and they're all facing the same direction. So I've made them rectangular because I want it to be clear that they are actually facing a direction. That's why we're also not using spheres. So this will be the face that they will turn toward our target. Okay, cool. Let's actually create our target as a sphere. So GGL grid shape. Draws to main. We don't need to set the shape as a sphere. So let's just maybe scale it a bit down. Make it a bit smaller. Yeah, 0.25 looks good. I want to have another GGL PBR, but I want it to be red. So I will set the color to red, and that is our target. This is going to be our spherical target. Real cool. Nope, not you, my friend. Okay, so now we want to get inside the jit.gen and actually start to work on the algorithm. Oh, I forgot one thing. Since we want to output the rotate attribute, which has 4 parameters, right? The angle and the axis, we actually need a matrix with 4 plane as an input, because otherwise we will not get a matrix with 4 plane as an output. Okay, so I just changed the number of planes here to 4. Because jit.gen outputs matrices that have the same plane amount and dimension as the input matrix. So we need to add 4 as the plane count instead of 3. And now inside the init position, what I want to do is to actually switch our x, y, and zeta here and just concat them to another number, which is going to be 1, because we want to set a 1 for the fourth. I don't know if this is really important, but we want to set 1 as the fourth component of this vector. It could be important for how the pipeline is rendering those cubes, but maybe it's not. Let's just do it. But the position and the scale are vertex attributes that only take 3 components. So what we could do is to actually unpack those matrices here with just 1 output and just jump the first 3 planes. This will make it then a 3-component, a 3-plane matrix. if I'm not mistaken. So if we go here and we check the planes, and we bang here, okay, so we can see that this is only 3 planes, while the matrix that was coming out would have had 4 planes. Okay, so this, we want to do this passage as well to get back to 3 planes. Cool, let's continuously bang this matrix as I said before. So let's receive this sender that I called the metro from the middle of the JIT world, which will send a bang at each frame. Looks good. Let's go back inside the algorithm. Let's actually now get in the meat of the algorithm. So what we want to do, since we only need the first 3 components, we don't really need the 1. So actually I should not have bothered setting it to 1 in the previous jit.gen, sorry about that. Anyway, we only need the first 3 components of this vector, the position of the cubes, and we need to get a vector that from the cubes or rectangles, whatever, goes toward our target. So to do that, let's create a param, let's call it target, and let's say that by default is in the center. So we need to calculate the vector that goes from the cubes to the target. We just need to subtract the position of the cubes to the target position. So this is the position of the cubes, let's remember that. Let's make a little bubble. And this is the target position, actually call it target pos, so it's kind of clearer. The underscore, which is more max like. And then we need to first normalize this vector, which will only give us the direction of the vector without the magnitude. And if you don't know what this means, I have a video about vector normalization, so I will link it in the description. And then we need to know what is the initial orientation of our cubes. Now, since we say that I want to use this face for getting them turned toward the target, we can assume that the vectors are that the cubes are all oriented toward the positive zeta axis, which is the axis that goes from the center toward us when the camera is in the default position. Okay, so we can assume that they are all oriented in that way, so we can create a vector. This represents the orientation of the cubes, and they are all facing toward the positive zeta axis direction. Cool. So what we have to do now is to make the cross product between the orientation of the cubes and the vector that goes from the cubes to the target. Okay, so the cross product will create a perpendicular vector that is perpendicular to these 2 vectors. Okay, so let's see graphically what this means. Let's make a little drawing here. So these are our axes x, y, and zeta. And we can consider that the position of the cubes is a vector. So let's say this is our cube. Its position is a vector that goes from the center to its position, right? And the position of the target, let's say this is our target here, it's a vector that goes, let's make it a bit darker, that goes from the center to the target position. Okay, and then we have another vector that is the vector that goes from the cube to the target, right? So this is our direction vector. Cool. Now, if we make the cross product between these 2 vectors, so the target vector and the direction vector, we will have a perpendicular vector to them that goes like here, in this direction, I believe. It could also go in that direction, depends which, if you invert the order of the operands here. But I believe as we put them, it will go in this direction. But I'm really not sure, actually, I should check this. I should double check that. But anyway, it's going to be a vector that is perpendicular to these 2 vectors. Cool, this will be the axis around which our cubes will have to rotate in order to face our target. Okay, so this is how we calculate the axis of rotation for these, for our cube to rotate toward the target. I hope this was clear enough. Cool, let's create a new output. This is going to be output 3, and this is going to be the rotate. This is going to be the angle plus axis of rotation. Let's make it really completely clear. Nice. And how do we find now the angle that our shape has to turn to face this target? Well, to get this angle, we just need to have the dot product between the direction vector and the target vector. So basically, if these both vectors are normalized, the dot product will give us the cosine of this angle. Pretty neat, right? And then we just need to rotate the cube on this axis on that angle amount. Sounds like magic, but it really works. I promise you. So let's do that. Let's do the dot product. The vectors need to be normalized for the dot product to work. Since this vector is always a magnitude of 1, we don't need really to normalize it. And also for the cross product, then it must be normalized. Okay, so this gives us the cosine of the angle between the two vectors. So in order to get the actual angle and not the cosine, we can use the arccos function, which will give us the arc cosine of the cosine, which is just the angle. And then we need to convert this to degrees because max works in degrees and not in radians. So this is the angle in radians. And then we want to concat the angle to this axis. Okay, so this is going to be our angle. This is going to be the axis. Cool. So this is the moment of the truth. Let's see if this actually works. Let's go in the patch, connect the third output to the second inlet. And yes, it seems like the cubes, our rectangles here, are facing the sphere. Very nice. Let's just move the sphere around a bit by using like a GGL handle. Connect it to the GGL grid shape here. And we can start to move our sphere around. Oh, and of course I need to get continuously the position of the sphere to send it as the target param. So let's receive the metro here, send it to the grid shape, and let's say trigger get position. So we'll always trigger the message get position, which will give us at every frame the position of the sphere. Now let's substitute position with target underscore pos, which is the name of our parameter in jit.gen. Cool. So let's move it around, and as you can see, these cubes will always face the sphere. That's pretty cool. Now, I want to have like lines that connect the sphere to the cubes, just to be completely sure that the lines are perpendicular to the face of the cubes. So in order to do that, I'm just going to create another a GGL mesh, which draws to main and has draw mode lines, and is of color red because I like red and white together. And cool, that's it. We now just need to get the matrix that has the position of the cubes, but also we need to interleave it with the position of the target. Otherwise, if we just do that, just get this matrix and use it as the position, it will just create the lines between the actual cubes themselves, right? So we don't want that. We want the lines to be created between the cubes and the sphere. So we can use like jit duplex or something. How is it called? I never remember. Multiplex, I believe, which will interleave two matrices. So if you check the help file, it will just basically put the content of one matrix and then the content of the second matrix in the next row, and then the first matrix in the next column, and then the next matrix in the next column. This is all it does. So that's exactly what we need, because if we then just root position here, so we get the row position, the three element of the position, and then we just get a JIT matrix with 3 planes, float 32 100 cells, and we say pack set all. Oh, actually, I don't want to use a pack because I want to use a message, because I want to also send a bang to this matrix, right? So we can do that, and cool, now all the lines are connected from the cubes to the sphere. Let's say if they are actually perpendicular to the targets, and it looks like they're exactly perpendicular to the faces of the cubes. Last thing, I want to arrange this cube in a sphere because I find it pretty neat. So inside here, the first jit.gen init position, what I'm going to do is to just normalize this vector, which is actually the initial noise. Actually, I want to do it, here. No, I actually want to do it after the mixing. So first I want to mix between -1 and 1. I want to normalize. I want to switch x, y, and z, and then I want to multiply by whatever. Here, load bang, and cool. Now they are arranged in a sphere, actually. Let's reset the position of our handle here. Cool, they are arranged in a sphere, and they all look toward the center. And if we move the sphere, they will look toward the sphere. Okay, so this is it. I hope you liked this video. If you liked it, like and subscribe to it will be very much appreciated. And if you want to download this patch and lots of other patches, check out my Patreon and check out also my website to check all my video tutorials and all the patches that I ever shared. And I will see you in the next video. Have fun and see you soon. Ciao.